Hello and welcome back to the Renewable Energy Technology course. This is the lecture series of wind turbines. I'm Miro and we are at the third lecture. Just some history, development timeline and soft issues related to wind power and wind power development. The second part for the lecture will focus on the first modern large prototype wind turbines. Not really the commercial ones yet, but these were really the machines that created or delivered the development. And it is very nice to learn to appreciate actually what people did and how they failed, because this is what actually helped to produce the modern development. One of the iconic machines from that time is exactly this one. We will come soon to it. Well, let's start with the multi-blade wind pumps. We are not going to talk about them a lot today. The other teacher for wind power in this course will stop longer at the wind pumps. But we should mention that definitely this was the first step towards the modern age of wind power. Moving from the four-bladed classic windmill rotor from the Middle Ages towards the industrial time, the link in between is exactly this type of machine. Very robust, very simple, very tough, very reliable design with a main purpose to pump water, usually with a long piston plunging pump, filling in a kind of a tank, just a reservoir just beside the mill, usually used in, well, open, arid, windy and waterless places. Very good help for the colonial times in the New World. And if you go there, you can still see some of those machines just left there for the stupid tourists. Of course, you immediately notice that there is no pump here. But that's how everything looked like. And this thing can still work if you really want it. There is nothing much to break. The blades are just curved plates. It can start while loaded. And it is so simple that anybody could do it, or at least maintain it, or produce it. Then we move on to the first attempt to produce electricity, and it's really a timeline here, or a turning point in wind turbine engineering, back to the classic four-bladed rotor, because that was the only thing that was known at that time. We're talking about the beginning of the 20th century, and a Danish guy with a peculiar name of Paul Lecour, who's actually managed to build this, and who was a teacher in rural Denmark in a kind of vocational school for farmers. He was using this, a kind of a lab, to teach his students in smithing skills. They were supposed actually to be farm smiths, so to say, workshop technicians. And they were supposed to be able to handle everything. Plus that, at that time, you know, Europe was already developing, while Denmark was without any fossil fuel resources, completely deforested. We're talking about more than 100 years ago, and wind-stricken, very poor in the countryside and rural territories, and people actually needed to use any kind of energy possible for any purpose possible. Many of Paul Lecour's students actually went on, including their sons and grandsons, to produce their own modern designs of small-scale windmills. And some of them actually participated in the modern age, in the middle of the 20th century, into the really industrial development of wind turbines. Paul Lecour even attempted water electrolysis more than 100 years ago. We are still talking about water electrolysis. Nobody's really doing it. With hydrogen storage. Hydrogen was interesting for the time for lighting. Nobody was driving engines on it. Lighting and heating, of course. And it was used inside the school, in the lab there, actually by all the students. Paul Lecour was so famous at that time that, you know, Albert Betz in the 20s in Germany who was a professor in the Technical University of Berlin, was using Paul Lecour's name and was giving him as a good example to his own students of what can be done just with common mechanical engineering knowledge without being a professor and so on, and how can wind turbines be improved at that time. Well, after Paul Lecour, all the theory of aerodynamics was developed at the time when aviation, modern aviation and the theory of wing profiles, propellers and so on was developed. After that, really, the modern wind turbines came to life, and the first one of the really large size using proper airfoil blades. You can see actually the wing profile here, and it does look like a simple airplane wing, was a turbine in Vermont in the United States in 1940. It was put in operation, and it actually managed to operate for quite some time by two guys. These are the two family names of the guys. You can check actually the text on your own. I have put a lot of text. It's very explanatory and tells the whole story on itself. Actually, those guys managed to produce a 53-meter rotor diameter. That would be like more than 25-meter blade. Big achievement for the time. Of course, the blade wasn't optimum. It was not twisted, definitely not tapered, and certainly not optimal for the application. It was a downwind machine, and these two guys actually triggered a kind of a trend towards the conception that the downwind style, well, the wind comes from here and hits the blades after the tower, is like a more reliable self-yawing or more well, sustainable, let's say, or resisting to vibrations and so on. Actually, it's exactly the opposite. They had a 1 megawatt synchronous generator, and it actually worked. Then we come to one of the most iconic devices of the modern time. In the 50s, this turbine survived until the 60s, even until the 70s, even until the 80s. It was still there and was able to operate. Not that big, 200 kilowatt turbine in Gedser in the southern tip of Denmark with a 24-meter rotor, developed by another iconic name and another strange, peculiar Danish name, Johannes Juel, who was a utility engineer and was very well schooled in exactly aerodynamics and grid connection and power engineering, everything that was necessary actually to put together a modern wind turbine. You can easily notice now the very proper engineered blades. Each section is actually dimensioned the way it should be. Still, in terms of mechanical construction, those blades were made more or less by hollow aluminum or, well, some kind of metal parts welded together. Johannes Juel easily noticed that the blades are not able or not reliable enough. They are not able to sustain all kinds of vibrations that they were loaded with. They were prone to fatigues, vibrations that were completely destroying everything else in the mechanical structure and so on. But still, he was the first to define the three-bladed, upwind, stall-controlled, you see now the first flap tip for the aerodynamic brake, design for the time, which actually lived long enough to be the first ever commercial turbine later on. It was the first possible commercial turbine, exactly this type of design. Johannes Juel worked with this turbine for a long time. He actually managed to improve it a lot, measure a lot around it, even stiffen the rotor with this very funky arrangement here. It's just a pole protruding from the hub straight ahead, and then a kind of a wire mesh connected from the pole towards all the blades, mechanically stiffening and making them a bit more resistant to vibrations. Especially with the blades and the electrical parts inside the machine, Johannes Juel was improving a lot and actually came up exactly with the modern so-called now Danish concept windmill that managed to start the commercial reality of wind power. Another very good Danish example, well, switching back to downwind type, but still a three-bladed rotor, now the first ever glass fiber blades, even if in the 70s they were still very new and experimental. Actually, these blades were changed once, maybe twice, The so-called twin turbine on the western coast of Denmark was built by a group of enthusiasts. It was not at all state-funded. Maybe it was, but at least the story says so. It had a 2-megawatt generator, the largest for the time. We're talking about the 70s, and the whole design, the whole project started in the 60s. And a 52-meter rotor. These were the first ever modern blades with modern materials that were attempted, and they proved to be very, very reliable. Well, quite expensive concrete-built towers. Otherwise, everything else inside was the typical Danish concept of a stall-controlled squirrel cage, short-circuited induction generator. Very, very robust machine. Then we're switching to other very interesting projects, and we don't have time actually to mention all of them. There are plenty of those, several in the United States, and in each of the industrialized countries there was at least one of such large prototype of wind turbine. One of the most important in the United States was in the 80s, the 78-meter, 4-megawatt rated capacity machine, the wind turbine system number 4, where Boeing was involved. Again, a downwind rotor, long enough blades, but very big, overrated electrical generator. This thing more or less never managed actually to operate for a long time with its rated capacity. But it was good for several purposes. First of all, this was the first modern tubular steel tower, and the tower was just perfect together with its foundation. Second, it showed actually that before building such monsters, actually you have to build and bring there out in the field the proper machines to put the things together. There were no such cranes in those days that could really build this thing out in the field. From that time, the development of cranes started, which were necessary for the wind turbines later on. We can move on to Sweden, even if the Swedish project actually passed quite unnoticed and didn't spark any attention. It was, interestingly, one of the most successful early prototype super large wind turbines. It did live for 11 years and was scrapped simply because nobody wanted to maintain it anymore. It did have a range of issues and problems, but actually it managed to operate quite reliably. It was again a 3-megawatt, approximately 100-meter rotor diameter in the 80s, downwind machine with 2 blades. The most risky design with 2 blades, proper tower, down on the southernmost tip of Sweden. And, well, there is no really nice picture of it. You cannot find anything better than that out on the internet. Then we step into the problem field. Very similar to the Maglarp turbine in Sweden, but much more a media hype project in Germany, very close to Hamburg, facing the North Sea coast, the so-called Grovian project. A 3-megawatt, 100-meter, that was supposed to be the most representative size for the time. Everybody wanted to have the 100-meter rotor. Downwind, 2-bladed machine. Well, not particularly beautiful, but that's no big issue. The big issue was that this thing didn't live more than several months. It costed a lot, you can imagine. It worked badly. It showed problems with blades, fatigue, bad performance, problems with the electrical connection, problems with the tower, problems with more or less everything you can imagine. Very unsuccessful, but, well, it was supported by an enormous group of German engineers and a whole state-funded project for not only one turbine, but more or less at that time, the beginning of the 80s, the end of the 70s, the modern wind turbine development in Germany that we know now was initiated. There were no turbines yet, but everything, all the theory was more or less done, not just for how to build machines, but how to develop everything, how to support the whole wind power development, where to install the turbines, how to actually take care of the stochastic or variable power output into the existing grid, and so on and so on. Good example, we have no chance to stop really there, from Canada. The biggest vertical axis lift type Darius rotor turbine in Quebec in the end of the 80s, 100-meter height with 64-meter rotor diameter. Well, we cannot say diameter because this is not a circle, but properly said it's the equator here had 64-meter span. 4.2 megawatt, the biggest rated capacity from the early prototypes. It actually worked fine, but it did show also some problems. First of all, typical for the vertical axis lift turbines, it is nice to have all the heavy equipment down on the ground, but there should also be a main bearing that supports everything. And that main bearing was failing all the time. The blades were also prone to fatigue, especially in the vertical axis wind turbines, peculiarly. And in the end, it was just too costly and scrapped. In the United States, there were several such vertical axis projects, slightly more successful, but more or less, well, ending up proving the same problems. And then we come to the most important example here. The Wind Energy Group, Orkney Island-based British project from the 80s. Well, it took 10 years to develop, more or less, and it costed 17 million pounds sterling. Let's repeat that. 17 million pounds sterling, 10 years development, and a lifetime of 3 months. Do you think that this poor thing could pay back for itself? Definitely not. And the target was not that it should pay back. It was supposed really to prove the concept, to show the problems, and yes, it did show the problems and the typical failures. First of all, this was a two-bladed rotor. From that point onwards, nobody ever tried to build two-bladed rotors. Very expensive tower, of course. A lot of mistakes done in the electrical infrastructure and so on and so on, the mechanical solutions. Big failure, enormous disaster. So what's the merit of all this? It was clear that big test prototypes were not the proper way to go. Everybody thought at that time that, okay, if fossil fuels get expensive, this was exactly the time of the oil crisis, we should start building wind turbines, and, well, we should definitely start building them big, of course. But big was not the answer. All of the industrialized countries had their own projects. The Danish ones, the most successful, not the biggest one, but the most successful. Everybody else also had some success. And definitely, the big result from all these early prototypes was that they very nicely showed the failures, the difficulties, the challenges with both mechanical design, blade aerodynamics, blade mechanical performance, aeroelasticity, and strength of materials, and so on. Reliable and low-cost solutions were required for the proper commercial reality of wind power. It wasn't yet there. Definitely none of these big projects could reach that point. Something else was necessary, and the answer is that evolution was necessary. From small reliable designs into larger and larger rotors, higher turbines, and higher rated capacities. It happened in Denmark. Again, some of the grandsons of the students of Paul Lecouvre actually, plus the Johannes Juul concept of the three-bladed, very reliable rotor with the simple electrical arrangement inside, produced the first turbines which were able to operate reliably in a commercial environment. They were generally up to 50 kilowatt, the first ones in the end of the 70s, beginning of the 80s. All of them produced by very small workshops, well, kind of factories out in the countryside in Denmark, which were supporting the agricultural sector, producing maybe other type of small machines, and being able to switch quickly into, well, making small wind turbines or putting from spare parts, some kind of a self-made wind turbine. Many of those designs were available in Denmark. Some of the names of those early companies are gone now, but they are exactly the ones which started the modern development of wind power. The first market started in California, and that's the topic for the next section. Quick summary of what we learned today. Well, first of all, the classic windmill rotor with the 4 blades definitely can also work for electrical generation. Why not? Many large experimental projects and test turbines were installed and developed. Many. Well, between 1940, after the Second World War, and until the very important time of the end of the 80s. Most of these early projects were a complete failure, a total disaster, a devastating failure. But they very nicely showed the major technical challenges or what needs to be solved for the proper development to occur. The very robust and reliable Danish concept with the 3-bladed upwind rotor and the induction generator inside was the only one that managed really to perform reliably in a commercial environment, and it was the first one to be used in real applications out in the field. We'll talk about it next section. Thank you.